Hello friends and welcome to our mechanical workshop. Now I explored the chance to introduce in front of yourself our final year project, that is design and fabrication of universal motorized gyroscope for laboratory setup. It has been made by me, Pothikrit Chatterjee, Arjun Kumar Chakraborty and Kaushik Pan under the supervision of Mr. Orijit Dotto and Dr. Sanchayan Mukherjee, members of faculty, Department of Mechanical Engineering, Kollani Government Engineering College. The main objective of our project is to design and fabricate universal motorized gyroscope as laboratory setup to perform experiments and analyze results. Now comes the introduction of gyroscope. A gyroscope is a device for measuring or maintaining orientation based on principles of angular momentum. A mechanical gyroscope is essentially a spinning wheel or a disc whose axle is free to take any orientation. The word gyroscope has been derived from the word gyroscopic couple. The theoretical approach of gyroscope consists of a rotor mounted in a frame of rings called gimbals, which are themselves supported on a spindle. Gyroscope can be very perplexing objects because they move in peculiar fashion and even seem to defy gravity. The applications of gyroscopes are turning in aeroplanes and rockets, scientific demonstration, computer pointing devices, racing cars, gyrocompass in submarines, anti-roll stabilizers and monorail trains. The scientific approach to this project is, this is a disc which is rotated with respect to this axis. This is further rotated with respect to this perpendicular axis, and thus a couple acts with respect to this third axis in this direction, and the system or the weight of the motor is balanced. While doing this, the L channel frame keeps on rotating about the horizontal axis. The speed of the gyroscope depends on the amount of RPM the motor generates. The amount of couple generated depends on the input RPM. The greater the input RPM, greater is the gyroscopic couple generated. The velocity of this fork is called the velocity of precision. Now comes the design approach. This is the rotor, this is the Y fork, this is the base plate, and these are the supporting L channel frame. Now comes the detailed specification. The rotor, the inner diameter of the rotor is 20 mm. The outer diameter of the rotor is 200 mm. Thickness is 45 mm. Mass is 3.78 kg. Moment of inertia is 0.076 kg per square meter. Material, mild steel. Now comes this fork. This fork is designed specifically for easy accessible than the gimbals, and we have cut out from a mild steel beams. Now comes this set of bevel gears. The gear ratio is 1:1. Number of teeth is 23. The face width is 20 mm. Module is 3. The shaft angle is 90 degree. Helical angle 0 degree. And the pressure angle is 20 degree. Now comes this radial ball bearings. These radial ball bearings or these radial ball bearings. These radial ball bearings we have used here in the sets of 6. Inner diameter is 15 mm, outer diameter is 35 mm, thickness is 10.85 mm. Now comes this set of thrust bearing as well as this set of thrust bearing here we have used. The inner diameter of this thrust bearing is 25 mm. The outer diameter of these thrust bearings are 37 mm. And now comes the L channel frame. The length of this L channel frame is 607.52 mm. The breadth is 306.86 mm. Dimension of this L channel frame is 20 into 2 square millimeter. Mass of the frame is 2.1 kg. And now we come to the assembly section. Now I am going to demonstrate the design of our gyroscope. We have used Autodesk Inventor Professional for designing, modeling as well as dynamic simulation of our machine. Now here comes the part designs. This is the modeling of our rotor. This is the modeling of our fork. This is the drawing of our fork. This is the modeling of the set of bevel gear. This is the part drawing of the set of bevel gears. This is the modeling of the radial bearings. This is the part drawing of the radial bearings. This is modeling of our thrust bearing. This is the part drawing of our thrust bearing. This is the modeling of the L channel frame. This is the part drawing of the L channel frame. This is the modeling of that base table. This is the part drawing of the base table. This is the modeling of the motor. This is the modeling of the weights. This is the assembly view 1. This is the assembly of the whole system view 2. This is another view of the whole system. And now comes the dynamic simulation. And we can see here how the machine gyroscope actually works. This is the end of the designing approach of gyroscope. Thank you Team Crazy Engineers for giving us the forum to showcase our talents. We have tried to put all our hard work to fabricate this setup. In design, we have tried to modify it from the traditional setup by using this L channel frame instead of a solid metal base. It is economically viable as well as we have reduced the weight by using this L channel frame. We have used a Y-shaped fork in place of a gimbal, which is easy to machine as well as we gain in strength. We have designed, machined, fabricated and assembled solely by ourselves. We have put in our knowledge of mechanics, strength of materials, manufacturing technology, material science, electrical machines and engineering economics to set up this gyroscope. Since we are yet to buy a variac, we are going to demonstrate this manually as our motor is nearly 1500 RPM. Now the gyroscope goes on like this. We are going on increasing speed and it is going to be balanced. For a constant speed, the gyroscope will not move like this. It will be balanced. We can see that the couple is active. Lastly, we thank all our teachers, our parents and everyone who inspired us as well as guided us to bring this in front of you. This is our gyroscope, the final year project of Kaushik Pan, Pothikprit Chatterjee and Arjun Kumar Chakraborty.